Hey everybody! In this video we're going to go over molecular polarity and how it relates to geometry. Before we get started, we probably need to make sure we go over some definitions. So the two definitions that we're going to look at is molecular polarity. And so what happens when a compound is asymmetric? It causes the molecule to have two different sides. And when something has two different sides, it has a pole. So it's like a magnet. A magnet has a north side and a south side. And so that is what we call polarity. Okay. And the north side is called the North Pole, and the south side is called the South Pole. Symmetry is when we look at a molecule and we see that it is symmetrical in many ways. Not just one way, but many different ways. So that's what we're really talking about in terms of symmetry and molecular structure. When we look at water, you'll see that it has 4 electron domains, and 2 of which are bonding. Okay, there's these 2 lone pair that are kind of covering each other up. But when we look at this guy and we think about it being symmetric, it is kind of symmetric, yes, this way. We can see it's kind of that way. But when we look and we reflect it this way, it's not symmetric. There's not atoms up here that are there. Okay, so we can't. This is not symmetric. So because it is not symmetric, we would call that polar. Okay. Now the conclusion that we draw is that any structure with 4 electron domains and 2 bonding domains is polar. Okay, that's really what we're talking about. Okay, and so that's what this video is going to do. It's going to go down through and give you the polarities of all of the electron and bonding domain combinations. So when we talk about here's the first one. Okay, there's 1 electron domain and 1 bonding domain, and is that polar? No. Okay, the reason for that is that this is always just one compound, and that's always going to be hydrogen. Okay, hydrogen is the only compound with 1 bonding domain and 1 electron domain. But we can look at other things like we can look at 2 and 1, 2 and 2, 3 and 1, 3 and 2, 3 and 3. So you can see the structures throughout here, whether they are polar, yes, for 3 and 2, or not polar, 3 and 3, 2 and 2. Okay, we will address these maybes in a minute. You'll see that the maybes happen whenever you have 1 bonding domain and however many electron domains. And all the linears may be polar or not. This is what you have when you have 1, 2, or 3 electron domains. And now this is what you have when you have the 4 electron domains. Okay, keep in mind there that the linear guy is maybe polar. We'll talk about that again in a minute. Okay, so 2 bonding, 3 bonding, 4 bonding domains. You can see that. Oh. I made a mistake, made a typo. Okay, so there's that. So there's 5 electron domains. You may want to pause the video and write these down. Okay, and then 6 electron domains. Again, pause the video and write them down so you know whether they are polar or not. So the question becomes, what about all those maybes? Well, the polarity rule is just about symmetry. We can go down through and make conclusions about these in general, but really, when you have something with just 1 bonding domain, we're really looking to see if a molecule is polar or is symmetric. So if we have something like this that's linear, Notice this guy is symmetric because it has the same atom on each side. So this guy is symmetric. So because both atoms are the same, the molecule is not polar. Now if we look at this molecule, this is HCl, notice that both the atoms are different. When the atoms are different, that means the molecule is polar. Okay, there's two different sides to it. Okay, so that's where all of those maybes come into play. Okay. So why do we worry about polarity and what's the importance of polarity? Well, as a general rule, polarity determines whether something is going to dissolve in something else. You guys may have heard that oil and water don't mix. Well, that's because one of them is polar, water, and oil is nonpolar, so they don't mix. So the general rule is like dissolves like. Things that are polar will dissolve in things that are polar. Things that are not polar will dissolve in things that are not polar. Okay, but oil is not polar. Water is polar, so because they're opposite, they don't mix. Okay, and so that's really what we're dealing with. So let's give some examples. Okay, so we look at this and we say, will carbon tetrachloride dissolve in water? So here is the structure of carbon tetrachloride. Okay, so in order to do this, we're going to go through and we're going to say that this thing has 4 electron domains. This thing has 4 bonding domains. And so we go back to the list. We look up what is 4 and 4. 4 electron domains, 4 bonding domains. This guy is not polar. Okay, 4 and 4 is not polar. So if it's not polar, guess what? This thing is not going to dissolve in water. Water is polar. Okay, this guy is not polar. So in order for them to dissolve in each other, they have to be the same. So this is opposite. The next example is carbon dioxide. And again, we look at this and we count electron domains and bonding domains. Again, this has 2 electron domains, 2 bonding domains. Everything so far seems to come back to these electron and bonding domain things. Okay, so 2 and 2, we look it up. This guy is not polar. Okay, so does it dissolve in water? It does not dissolve in water because this guy is not polar. Okay, in order to dissolve in water, it has to be polar. Water's polar, whatever would dissolve in it is polar. This guy is not polar. You know how I know it doesn't dissolve in water? Because carbon dioxide is what they use to carbonate soda. And what happens when you open up soda? It fizzes. That's because the carbon dioxide is trapped in there and then it releases. It doesn't dissolve in the water. It just gets released when you open up a soda bottle. So carbon dioxide does not dissolve in water. Okay. So this is your video on polarity. Make sure you write down all the things, whether they are polar or are not polar in terms of the number of electron and bonding domains. Okay. Have a great day, everybody.